talk, first we'll discuss two data structures, very simple data structures, but very widely used. It's stacks and queues. So what is stack? Stack is a very simple data structure. It looks like this. Change the marker. And you put elements in this stack, this, and you have two operations. You can put a new element on top of the stack. This operation called push. And you can get element from the top of the stack. It's called pop. What is the name of the cat? I don't know. It's you decide. Just. For example, we have three elements. We have A, B, and C. So we push these elements, like we say, push A, then push B, and then push C. And then when you pop the element, you get the topmost element of the stack. So when you pop the element, you will get this element C. And element C will be removed from the stack. So this function returns the element C and removes this element from the stack. Artyom, why not? Now, how to implement this data structure? It's very simple when you have a big array. Let's say we have an array of infinite sites. So we have infinite array. Infinite array. Let's call it array A. I always call arrays A when I can. If I have two arrays, I call them A and B usually. I'm not very creative in this part. Okay, and we will put this element from the left of this array. So the indexes of this element will be 0, 1, 2, and so on. So we put element A here, element B here, element C here. That's all. Let's look on the indices of this element. So if we have n elements in the stack, they will have indices. So if we have n elements here, they will have indices from 0 to n minus 1. That's basically the whole plan. Now let's implement these two functions. Function push x. So when you insert new element in the stack, you put this element in this position. So you put the new element here and increase n. So we need to put new element to position n and then increase n. So I'll say just a. Let's say that n plus plus equal x. That's exactly like we did when we had binary heaps. Yeah, like you put the element in the last position of the array. And when you pop the element, we need to simply return the last element of the stack and decrease n. So let's say return a minus minus n. That's all. That's the whole stack. So it's a really simple data structure, but it's widely used in various different problems. For example, even if you didn't implement the stack by yourself, never. So you may use stacks when you have any recursive procedure. So when you implement recursion in your program, like you say you have like function f, of, let's say, n. And somewhere here you have call of f from n minus 1. And somewhere here return. Something like that. So when you have a function which calls itself. So what happens when you implement, when computer tries to implement your program? What happens? It starts from function f, so it remembers the state of variable n. So let's have f of, let's say, of 10. So the computer should remember that the value of n equals to 10. And you may have some local variables, like we have like I equal to n plus 5 and so on. So you have some local variables here. So your computer needs to store these values of the local variables as well. So you need to remember that I equals to 15 and so on. So you remember all the values of all the local variables. And now when you make the call of f of n minus 1, you make another recursive call. So you have f of 9. And for this recursive call, you also need to store all the values of these local variables. So here you have another, n equals to 9, I equals to 14, and so on. And then you go back from this recursive call, you need to go back to these values of all the local variables. So the computer needs to store all the values of local variables for all recursive calls. And the computer does it using stack. So you have a stack of these blocks. It's called stack frame. So you have a stack of blocks of values of local variables. And when you go deeply in the recursion, you push another block of these variables in the stack. And when you return from the recursive procedure, you go back to this block of variables and so on. No, the computer only lost these variables when you return from the function. When you return from the function, you lost this block. Yeah, but you need to go back to the previous block. So if you call this recursive function from this recursive function, you need to go back from this recursive call to the initial call of recursive function. So you need to go back to these values, so you can just lose them. That's basically how it works. Also, you need Also, you need to get the pointer to the position when you go back. So you need to get this position and store this position p to somewhere. So when you go back to recursion, you need to know from which point of the procedure to continue the execution of the program. That's how it works. So even if you didn't implement stacks by yourself, you did use stacks when you use recursive procedures. Fine. Now the next data structure is queue. Queue is again a very simple data structure. So it's just the list of elements. Let's say A, B, C. And you put the elements from one end. I'll just call it add. There are different names for this function. I'll just call it add because I cannot pronounce most of them. Add is a simple name. And you remove elements from here. And here, for example, you add A, then you add B, then you add C, that's too much. And then you remove, when you remove the element, you remove the first element which you add in the set, in the queue. So you will remove this first element A and return this element. That's all. So these two ends of the queue are usually called head and tail of the queue. So this end called the head of the queue. Here are the And this one called the tail of the queue. I have problem with letters today. That's, anatomically speaking, is kind of strange. So you add elements to the tail and you remove elements from the head. But this just names from the queue, like when you have a queue to the shop or something like that. So you have what you have. You have like a shopping window here, and you have the queue of people who wants to buy something. So your new element will be added to the tail of the queue, and when you then it's your turn. You just take the first person in the queue and remove this person from the queue. That's all. That's all. The queue is mostly used when you need a queue. So, for example, if you have some tasks queue, so you have some tasks and you have some workers. So there are workers who will take the tasks from the queue and execute these tasks. And there are some other elements of your program who will add the tasks to the queue. So you have some workers who will process these tasks and some other, let's say, workers who will add new tasks to the queue. And so on. Fine. So how to implement this queue using arrays? Again, we will have a big array. Let's say we have very big array, like of infinite size. And we will have 2 pointers in this array. First pointers will point, the head will point to the first element of the queue, and tail will be pointer to the first empty element of the queue. So head is pointers to this element, and tail points to this element. That's all. Yeah. So elements of the queue have indices from head to tail -1. That's all. Now let's just implement these two functions. So we need add and remove. Can I get here? Yeah, I think it's enough here. So how to add element to the queue? So the new element we should add to this position of the queue, to the position tail, and then increase tail. So let's say a tail ++ equal to x. It's very simple. Yeah. And how to remove elements? So to remove element from the queue, we just need to take this first element with position head, remove this element, and move head to the next position. Head ++, right? That's all. Nice. That's all data structures for today. Basically, today we will learn 2 data structures: stacks and queues. That's all. Actually, also we have decks. Like there is another special data structure. It's called deck. It's like the union of these two data structures. So imagine you have elements in the list, and you can add and remove elements from both ends of this array. So you can add and remove elements from here. You can add and remove elements from here. For example, in C++, you have like this batch structure. You can make deck of something, and you will have these 4 procedures like push. To the left, it's forward, I think. Push forward. Pop forward. And here we have push back. X. And here we have pop back. So when you're not sure what data structure you need, you may just use deck. So you can add and remove elements from both ends of this list. Push front, yes, my bad. Thanks. Also, you have in C++, again, you have data structure vector. And for vector is basically a stack. So you can push back and pop back, and you don't have these procedures. So if you have C++, you don't need to implement all this. It's not a big problem to implement this, but even if you don't want to implement this, you can just use this data structure. That's basically all. Now, what will we talk about today? When we was implementing these data structures, I said that I will imagine that we have an infinite array. And infinite arrays usually don't exist. So usually in the real program, you don't have any infinite array. So you have some array of fixed size. And it's kind of complicated what to do when you have only arrays of the fixed size. For example, for the stack, it's a little bit smaller problem, because for a stack, if you know the maximal size of the stack you will have in your program, you can reserve the amount of memory equal to the maximal possible size of the stack. For the queue, it's a little bit more complicated, because even if you know the maximal possible size of the queue, then when you execute these two procedures, the queue will move to the right. So you have this array. So you reserve some big array, but then you add elements to the tail and remove elements from the head. And this queue will move to the right. So you will add element here, remove element here. So at some point you will reach the right border of the array. You never use stacks, but can execute them. Yes, you can use deck instead of stacks everywhere. If you know how to implement decks, you can just use deck. That's right. And you can use deck instead of queue. I think next lesson we will talk about why sometimes you need simpler data structure. So sometimes it's good to have more simple data structure, because it's easier to analyze data structure, it's easier to make some unifications and so on. So sometimes it's a good thing to have simple data structure instead of complicated data structure. So sometimes you actually want to use stack instead of deck, because stack is simple and you know what's happening in the stack, and you like don't really know what's happening in deck. So if you want to add some additional operations, you may want to use stack instead of decks. But if you just need normal stack, you can use deck instead, and that will be fine. You just don't use these two operations. That's all. What I was talking about? So if you use this big array for the queue will move to the right border of the array, and so at some point you will reach this border and you will have some array index out of bounds exception or something like that. How it's called in C++, you know. So you will go beyond the size of the array. So how to fix this? It's actually pretty simple. You can make the array cyclic. So when you let's say you add some elements here, then you remove elements to the left, then add more elements here, and elements here, and elements here. So at some point you reach the right border of your array. You can just go to the beginning of the array and continue to add elements to this part. So you just start from here. So your head is here, and your tail is here. The changes are pretty simple. I don't want to do this. Can you implement by yourself? It's pretty simple. So when you move these pointers, you just need to get them modulo n, so modulo size of the array. So if the size of the array, here you have plus plus, and then take it modulo the size of the array. And here so on. That's all. That's how you solve the problem with the queue. So the queue is moving. It's actually not a big problem. So if your queue is moving, you just need to make the array cyclic. So the size of the array should be equal to the maximal possible number of elements in the queue. Cool. Now let's go to the big problem. What is the deck? The deck is a like mix of stack and the queue. Like here is the deck. So you can add and remove elements from both ends of the queue of the deck. Deck is basically a double-ended queue. So you can add, remove elements from both ends. Now, let's go to the major problem. The major problem is that usually you don't know the maximal possible size of the stack. Let's go back to the stacks. So you want to implement the stack, but you don't know how many elements you will be pushed in the stack. So you cannot reserve enough array. And even if you know the maximal possible size of the stack, you usually don't want to spend this many memories. So usually what you know that the size of the stack will be no more than, let's say, 1,000 elements. But that's the total maximal possible size of the stack. But usually the size of the stack is about 10 elements. So if you reserve 1,000 elements for your array, you will always have most part of the array empty. That's not good. That's not efficient for the memory. So what you want to do is to have small array when you have small number of elements and big array when you have big number of elements. How to implement that? Oh, that's an exercise for you. That's quite simple. You just combine these two techniques. No, you do the same, but you have this tail and queue, and you need to have two additional functions here. When you want to push front, you just move head to the left and put element here. When you pop from the front, you take element. When you pop, no, I have pop front. I don't have pop back. When you pop element from the back, you just move tail and pop this element. That's an exercise for you. Yeah. Now we will talk about. But if you have vector in C++, for example, or you have lists in Python or something like that, so in most common programming languages, you have some way to implement the stacks. In Python, you can append elements to the list, and it will be increased. You can implement this using linked list, but we will talk about next time. Another way to solve it is to use linked lists. We will talk about linked lists next lecture. Today we'll talk about how to implement it using arrays. Let's go back. So when you have vector in C++, it somehow changes the size of the array based on the number of elements in the stack. So how vector works? It works pretty simple. Let's raise something. Let's clear something. Let's clear this left. Let's do it in the following way. let's have a small array. Let's have, for example, array of size 2. So let's reserve 2 elements for the array. Now we'll push elements in a stack. Let's implement only push operations. We'll talk about pop operations later. So let's have push operation. So you push the first element in the stack. So now this element is occupied. Now you push another element in the stack. And now when you push the third element in the stack, you see that the array is full. So you have no empty space for the next element. So what you will do, you will create another array. Let's say this array A. Let's create another array of bigger size. And then you copy the elements from the previous array. So you copy these elements to the new array. And now you have space for the next element to push. So we push the next element, you push element here. That's all. That's what happened when you push the element in the vector and the array is full. So it actually works like this. It creates new array. It copies the element from this array to the new array and then add the new element here. Now, what should be the size of this new array? So let's say the size of this array was n. What should be the size of this array? For example, what happens if you increase size by 1? Okay, it's logical. You need one more element in the array. So if you make array of size n plus 1, what will happen? Any thoughts? Yeah, that's correct. Yes. The problem is when you if you increase the size by 1, you will need to increase the size on each call of push operation. So each time you push a new element, you need to increase the size of the array. So each time you need to copy all elements to the new array. So all calls of push will cost you big O of n time. So each time you need to copy these elements here, that costs you linear number of operations. So it's not good. Instead of making n plus 1, we will say we have array of size, let's say 2n. n is actually not in practice. Sometimes it's you make arrays not 2n but 1.5 and something like that. So, but I will say we'll have 2n. So it's enough to increase the size by some constant factor. So increase n by multiplying the size by some constant. 2 is enough. Now let's just write the code. So what we have? We have this number n. So if the array is full, if n equal to size of the array, then we will create a new array. This. Let's create a new array. Array of size 2n. Then copy all elements from A to A prime. Let's see, copy. Let's say like this from A. Let's write that like this. Let's say A prime from 0 to n minus 1 equal A from 0 to n. It's like special operation to copy this part of the array. And just assign it to A. That's all. That's how you extend the size of the array. And now you have this. We have this to push this element x. So let's say now A n plus plus equals x. That's all. That's the modified push operation. Fine. Now, what is the time complexity of this function? In the worst case, again, Windows kernel you need to do it manually. Windows kernel allow you to get this array of size to n pretty fast, but it will not increase the size by. So you need to do it manually. Maybe there is a way to make the Windows to do it for you. I'm not sure about this. No, I don't think Windows can do it automatically. No, because you need to change the position. Yeah, I think Windows will not do it automatically. Again, what is the time complexity? And again, worst time complexity will be big O of n. So this part works in linear time, and this part works in constant time. So in the worst case, then array is full. You need to spend linear time of operation to insert new element in the stack. But this happens not very often. Let's think about it. So what happens here? So you increase the size of the array to 4. Now you add these two elements to the stack, and then you need another expansion of the array. So you create another array of 8 elements. With 8 elements. You copy these elements here. And so on. So the picture is like this. If you look on the time of each operation, it works like this. So you have here you have 2 fast operations, then you have 1 slow operation. Then you have another 2 fast operations, then 1 slow operation. Then you will have another 4 fast operations, and then 1 slow operation, and so on. So some operations are slow and some operations are fast. And what we want to analyze, it's kind of like that. There are slow operations, but they are pretty rare. So sometimes you need to make slow operations, but not all the time. So what we want is to analyze like the average time of operation. So if we look on the average time of operations, it should be pretty small, kinda. It's just want to give you some intuition about what we're doing here. We want to calculate like the average time of operation. So, for example, if you make n operations, so if you make for I from 0 to n minus 1, push I. What will be the total time of all these operations? So, if you make a big number of operations, what will be the total time of all these operations? And to analyze data structures like this, which have sometimes fast operations, sometimes slow operations, there is a special technique which is called amortized analysis. Let's put it here. Okay. Do I pronounce it right? Look fine. Yeah, I can spell it right. Fine. So, what is the idea? What is the idea? let's look on our data structure. So each operation in our data structure have some working time. So we have some real-time complexity. Let's see, this T of operation, it's real-time complexity. And we will add one more function. Let's say this amortized T. It will be the amortized time. Amortized time is something that you need to just get by yourself. So it's not the property of the real operation. It's like more virtual thing. So you need to get some. It's some. Let's say it's some upper bound on the average time of the operation. So you need somehow to to put some function here and then to prove this function is right. What doesn't mean that this amortized time is right? The amortized time is right when the following property is satisfied. If you have like a big number of operations, so you have empty data structure and then you perform some number of operations. You have some operations O1, O2, O3, and so on. Let's say M operations. What you need a total real time, the sum of all real time, be no more than the total amortized time. For example, let's go back here. So if this is the real time, this is the amortized time. So what we want to do is like the even the all times of all these operations. So we want to like make something more evenly distributed. So we have some. What is number of operations? Like 2, 3, 4, 5, 6, 8, 9, 10, 12. So we have. So what we want to have something like that. And if you look on each prefix of this sequence, like here you have 5 operations here. So if you have these 5 operations and you have these 5 operations, 3, 4, 5. This sum should be no more than this sum for all prefixes of this sequence. If this property is satisfied, we will say that this amortized time is good. Okay, that's all. So again, what we'll do, we will look on our function and we will say that we think that amortized time should be about like this. And then we will prove that this property is satisfied. And if this property is satisfied, we'll say, okay, this is the right amortized time of this operation. That's all. Let's go. What I want to prove now let's prove that we can assign some constant amortized time to the function push, and it will be correct. So let's prove this for this function. We can say that the amortized time, for this function, let's prove that the amortized time is constant. How to prove this? To prove this, we need to prove this property. So we need to prove that for each prefix, if we make some sequence operations, the total time of these operations for I from 0 to m minus 1, let's say, the total time should be no more than some constant. So again, if we want to prove that amortized time is constant, it should be, let's push, no more than C. Let's say just equal C. Why not more? Let's equal C. C. So if I want to prove that amortized time of the push equal to C, I need to prove that for each sequence of consecutive operations, the total time of these operations will be no more than this sum. And this sum is just sum of m times each equal to C. So this sum equals to C multiplied by m. So if I want to prove that the time complexity, amortized time complexity of this function is constant, I just need to prove this fact. I need to prove that for each sequence of m operations, total time complexity will be no more than C multiplied by m. That's all. That's just by definition of amortized time. Sigma, I don't need any sigmas here. I don't get it. I don't have any sigmas here. I don't get it. I don't have any. This sigma. Oh, that's fine. That's right. Yes. My bad. I forgot this sum. We know more than this sum. Of course. Yeah. Thank you for pointing. Yeah, that's right. That's all. Let's prove this. There are different ways to analyze the amortized cost of the data structures. The most naive way to analyze the structure is just by definition. So let's just look on our function, use this definition of the amortized cost, and prove that we can assign this constant amortized cost to operation push, so that this sum will be no more than C multiplied by m. To do this, let's just look on this sum. So let's look on our function and calculate the total number, total time of m operations. So if we perform, let's go here. So if we perform m operations on our data structure, what will be the total time cost of this operation? So let's calculate the total time of m operations. Well, let's say if we push m elements in the stack one by one, what will be the time complexity? Well, let's say we'll spend m operations here. So move this. So here we will spend like m operations. So each time we will go to this line and insert new element in the stack. We can say 2m, like if we have two operations, but constant factor is not important. So let's say we have m operations here, plus we have some operations here to copy elements to the new array. So how much time do we spend when we copy elements to the new array? Well, let's look. So each time, so we start from the array of size 1, let's say. Now we increase the size and copy this element here. Now we increase the size and copy these two elements here. And now again we increase the size and copy 4 elements here. So how much time do we spend on this copying of the elements? So we spend 1 operation here, 2 operations here, 4 operations here. Well, let's say and so on. So this will be the final state of the array. So in the final copy, we'll I don't want to make it too long. let's just say this is 2 in the power of k. Yeah, good enough. So first time when we expand the size of array, we spend one operation just to copy one element. Then we need to copy 2 elements, then we need to copy 4 elements, then 8 elements, and so on. So these are the costs of this copying function, this function. So what will be the sum of this copying? So we need to calculate the sum of this 1 plus 2 plus 4 plus and so on plus 2 in the power of k. Well, this is simple. This is the sum of geometrical progression. It will be equal to 2 in the power of k plus 1 minus 1. Now, how this k corresponds to the value of n? How it corresponds to this number of operations we need to, when we increase the size of array, to this number of elements in the array. Let's see. So when we make this last copying of the array, we have all these elements full. So the number of operations in this number of elements in the stack will be at least 2 in the power of k. So this 2 in the power of k plus 1 is no more than n 2n, right? Why n if I have m? M, right? I have m operations. Right, that's better. So the total number of operations we spend on copying this element to new array equal to is no more than 2m. So this sum will be no more than m plus 2m equal to 3m. That's all. So now we go back to what we need to prove. If we take c equal to 3, then we need to prove that the sum is no more than 3m. We just prove this. That's all. Any questions by now? Okay. Why 3m? Because m plus 2m equals to 3m. Again, this m comes from this part. So each time we call push, we need to call this line, and this line just spends a constant number of operations. So we spend like m operations just executing this line. And to execute this line, we need like n operations. So the total number of operations we spend here is 2n, no more. So top 3n. Fine. So that's the first way how you prove your amortized cost of the operations. This paging makes it more unpredictable. Calculate amortized cost. What is paging? You mean that we cannot just allocate this rate, or what? No, here I assume that I can allocate the array of any size in constant time. In practice, it's not exactly true, but I just assume that I can make this operation in constant time. Yeah, that's almost true. Almost, not exactly. But I'll think that I can allocate any array in constant time, and I will not think about this. Next. So this is the first way how do you prove your amortized cost, but it's not very comfortable technique, because if this function is very simple, so we just need to analyze very simple data structure. If data structure is more complicated, you need and you try to calculate this sum, it will be a mess. So there are more comfortable and useful way to analyze the amortized cost of your data structure. First way, let's draw something here. What can I erase? Which lines have m complexity, so the total block makes up to m? Yeah. I don't get it. So this line takes constant number of operations each time. So total number of executing this line will be m. The creation of new array is cost you the sum of this geometrical progression. So this sum is no more than 2m. So the total time you spend on copying elements to the new array is no more than 2m. So you have m here and 2m here. Again, I calculate the total time of all calls of the push function. So I call push function m times, and I want to calculate the total time complexity of these m calls. So I calculate not a single execution, but the sum of all executions. So if you call push m times, you will need to extend arrays this many times. So the total time you need to spend to expand the size of the array. Oh, fine. Nice. Nice. So the next technique, very useful technique, and we will use it later in much more complicated data structures. It's called the potentials. We need to add. What should I remove? Let's remove this. Actually, I can remove this code. I don't think you need this code to analyze this data structure. It's too simple. Can you use it in multidimensional arrays? You can use the same technique in multidimensional arrays. It's a little bit more tricky, but yes, you can. You need to think what actually you need to do with the multidimensional arrays. Like when you increase the size of the multidimensional array, you need to increase the size by 1 dimension. You can do it in the same way, but you will. No. Basic answer: you can do it in multidimensional array, but you need to think what you actually plan to do with the multidimensionals. Potentials. Let's add some special potential function to our data structure. This potential will be some value assigned to the current state of the data structure. It will be simple. So we perform these operations on data structure. So again, let's have operations 1, 4, 2, 3, 4, and so on. So before the first operation, we have some value of the potential. So it's value of the empty data structure. So here is v0. Now we make the first operation, and we have another state of the data structure. So we have potential equal to v1. Here we have v2, v3, and so on. Here we have vl. So this potential function corresponds to the current state of the data structure. It somehow expresses how bad is your state of data structure, something like that. That's all. We will have two properties on potential function. We will say that the initial value of potential equal to 0, and potential will always be non-negative. again, this potential is not the property of your program. So you can't just get this potential from your program. You need to somehow get this potential from your head. So you just look on this program, see what may be the potential function, and then use this potential to prove your amortized cost. We'll go to it just very soon. What is the plan? The plan is, when you fix your potential function, you go here and you say that the amortized cost of the operation will be equal to the sum of two values, so to the real cost of the operation plus the change of the potential. This is equal to like phi of I plus 1 minus phi of I. That's all. And now let's prove that if we have this potential function and we just define the amortized cost using this formula, we will get the correct amortized cost of the operation. So if you fix something like that and you use amortized cost like that, you don't need to prove this inequality, because this inequality will satisfy it. Why? Let's go back to this inequality. Let's see, what is the sum of the amortized cost? So let's see, what is the sum of the amortized cost of all operations? This will be the sum of real costs plus change of the potential. Now, if you sum all changes of the potential function, you will have the final change of the potential function. So this will equal to the sum of all real costs plus this change m minus E0. Yeah. And this value is non-negative. So we just prove that the total amortized cost is greater or equal than total real costs. That's exactly what we need to prove here. Run it here. So again, what is the technique? Instead of just putting some amortized time and then proving this sum, you fix some potential function and then use these amortized costs. And then you don't need to prove this inequality because it will be satisfied. Let's stop. Okay, how to find a good potential function? That's the most important question. So if you want to analyze the amortized cost of your data structure, you need to find some good potential function. So if you feel like your data structure is working good on average, you need to find some value which can be assigned to the potential such that if you get this amortized cost, it will be small. So that's the intellectual part. So you need to get some intuition about what happens to your data structure to find the good potential function. For example, in our stack, what happens? How to find a good potential function? Very simple. Let's look what happens when you have some slow operation. So when we have some slow operation, happens something like that. We have some full array, and then we copy elements to this array. So we copy these elements here. So we spend like n operations to copy these elements. And if we want the amortized cost to be small, so we want this amortized cost to be small, and this t equals to n. So we want this sum to be small. So we want this change of potential be about minus n. So if we have, let's say, here we have like phi1, here we have phi2. This change of potential, this phi2 minus phi1, should be about n, minus n. Just to compensate this real time. So here we have, again, this equal to n. This should be no more than some constant. So we need to add something to this n to have some constant value. So this change of the potential should be about minus n plus some constant. Now, how to find the good potential function? We need to look on this picture and see. So we need some function which in this case is big. So we need something with here is big and here is small. So that this difference will be about minus n. That's kind of intuition you want to have when you want to find a good potential function. Well, let's find it. So we need to, again, how to find a good potential function? You just look on this picture and find something which is small here but big here. And if you look on this picture long enough, you kind of figure out that in this picture you have empty space here, and in this picture you don't have empty space here. So let's look on the right part of this array. So let's look on this part of the array. In this situation, this right part is filled with elements, and in this situation it's empty. So if we say that the potential equals to number of elements in the right part of the array, like in this part. So here we have about n over 2 elements here, and here we have 0 elements. So this change will be about minus n over 2. But we need to make it minus n. So it's quite simple. So how to make it minus n? We just multiply it by 2. Just multiply this by 2. And this will be our potential function. So now, if we use this function as our potential function, what we'll have? In this situation, we have, again, I'll erase this. We have time equal to n and change of potential equal to minus n. So we spend n operations to perform this copying of elements, and we decrease the potential by n. So this amortized cost will be constant. That's all basically. That's how potentials work. Again, we will use potentials later in this course pretty often. So it's a very powerful technique. When you need to analyze the amortized cost, you just get this potential from somewhere and then prove that if you use this potential, then the amortized cost will be small. Very nice technique. Very nice. The only problem is to find the good potential function, and that's how you do it basically. You try to find the function which is decreasing when you make some slow operation. That's the that needs kind of intellectual work. Fine. And another that's very powerful technique, but it needs some insight about how to get this potential function. There is another technique that is basically does the same, but it's kind of more visual, so it's kind of easier to think about it when you knew about amortized data structures. It's called I don't know right term in English. It's like a bank account technique. I know. Sorry, I just googled the right term in English. Just it's called accounter method or bankers method. Okay, accounting method. Okay, nice. I didn't know the right term in English. Sorry. So it's called accounting method. Let's raise something. Can I raise this? I don't need this. I need this in equation, but I don't need that. Just write this in equation again here. You remember the equation, right? So. Accounting method. What is the idea? Imagine you have some bank account and you can just put some time in this account. So you have two operations just to put a coin in your account. Let's say T. That's time. And remove a coin. Get coins, let's say. So you have some account which stores your reserved time. And you have two additional operations. You can reserve some time for future. To reserve some time, you spend this time. So for this operation, the amortized cost is T. And you can get some time from your reserved bank account. So you can go to your bank account and say, I reserved some time before. I need this time to make this long operation. So you use this reserved time to make long operations. So get so the amortized cost of this operation will be minus T. That's all. And again, this method is very visual. So I'll just draw a picture, and I'll draw a coin of size T for any operation put coin. Let's go back here. Let's move everything here. I'll just draw the same picture again, actually. How it works? So you have again, you have some array. Let's start with array of size 1. So we have array of size 1. We put the element x here. And let's add some put coin here. So each time we put new element in the stack, let's save some time for future. Just so put the coin of size 1 here. Now, when we need to add one more element here, we need to copy this element to the new array. So we get the new array, and we need to copy this element to this array. And we copy this element using this reserved time. So we go to the bank account, take this time from the bank account, and use this time to copy this element here. So we spend this coin and copy this element to the new array. Now we add another element here, and we put another coin here. Now it's a little bit more tricky. So we need to use this coin to copy these two elements. So we will put coin of size 2. Let's just always put coin of size 2, just for simplicity. So we use this coin and copy these two elements to this new array of size 4. Again, we use this coin. Here I say get coin. Okay. Coin of size n. So we take these two elements and copy them here. And so on. Now each time we add new elements to the stack, we add these coins on top of each element. And now when we need to copy this element, this array to the new array, we reserved here, we've reserved n over 2 coins of size 2. Of size 2. I don't know what happened. Sorry, when it happened? Again, I'll repeat. So what happens? Each time we add new element to the stack, we put a coin of size 2 on top of this element using this operation. And now when we need to copy these elements to the new array, we have n over 2 coins of size 2. So we have n total coins stored in our bank account. We just take this n time and use this n time to copy elements to the new array. So here we take these coins and copy elements to the new array. So here we have n operations. And we make these operations using these coins. So we take these coins from a bank account and use this saved time to copy elements to the new array. That's all. That's how simple it works. Now, let's analyze the amortized cost. Again, here we spend n operations, and here we have get coin, which costs minus n operations. Here we spend 2 operations, and here we spend 1 operation. So the total amortized cost of this push will be 3, like before. That's all. If you compare this technique with the potential technique we used before, it's kind of the same. So if you look about what function we had as a potential before, we used the function which was the number of elements in the right part of the array multiplied by 2. And here we have about the same thing. Here we have on each element in the right part of the array, we have coin of size 2. So the total number of these coins will be 2 multiplied by the number of elements in the right part of the array. So we just did the same thing as we did before using the potential technique. But the technique with potentials is a little bit more universal. Because here you need to put some coins somewhere, so you need to remember which parts of your data structure have some coins. In this technique with potentials, you can use even non-integer potentials. So we will talk about data structures we have non-integer potential function. So this potential function is just a function of the current, it just describes the current state of your data structure. So it shouldn't be integer, it shouldn't be put in some part of your data structure. It's just some function of your current state. Here you have some more visual thing. You have some coins. You know where are the coins in your data structure, so you can just analyze how you operate these coins, where you get them and where you put them, and so on. So it's just very visual, very visual technique. It's not that universal, but it can be used in most cases when you need to analyze the amortized cost of data structure. Okay, let's have some final words. First, we analyzed only the push function of the stack, but we also have the pop function. So this is the push function, and we also have the pop function. How can we implement the pop function? First, idea is you can implement a pop function like before. So you can just say turn minus minus like this. You can do it like this, and it will actually work. So you just take the last element, remove it from the array, and so on. But the problem is, again, when you have a lot of empty space in your array. So if at some point you push too many elements in your stack, you increase the size of the array too much, and then you pop all these elements from the stack. So you have elements only here, and here we have a lot of empty space in your array. This may happen. So to avoid situations like this, we need sometimes not only to increase the size, but sometimes you need to decrease the size of the array. So you need some technique to get from big array to small array back. How to do it? Well, let's say we have something like that. So let's remove the element from the stack. So in the end, I will return this. And here, same. So here, what I want to do is to look if the size of the stack is too small, then I will decrease the size of the array. So if n is less than something, I want to create the smaller array. So I will create the array twice as small as the current size. Let's say a size, and then again copy the elements like this. So I want to decrease the size of the array twice. I have this big array, I want to move to this smaller. And the interesting part is what condition we need to have here. So if I have something like that, so if I say that if number is smaller than the size of the array, so if I have less than half of elements of the array filled with elements, and I will just create the array of twice smaller size and copy these elements here. What will happen? What will happen if I have these two procedures? Many guesses? The inverse is what happened before, but what happened before? I want, what do I want? I want both operations to have amortized cost equal to some constant. So I want the amortized cost of both operations be constant, and amortized cost of pop operations to be constant. Will the amortized cost be constant for these two functions if I have this condition here? No, actually, it won't be constant. Why it happens? Because you may have situation when all operations take linear time. So you have the sequence of operations, and each consequent operations need you either to increase the size of array or to decrease the size of array. So if you have the number of elements about the middle of the size of the array, so here you take from this array to here. Now you make push operation, so you add, so here you have pop operation. Now you make push operation, you add these elements here, you have not enough space here, so you need to increase the size of the array back. So you need to spend another n time to copy elements here. So if the number of elements is about this point when you need to change the size of the array, then each time or pop or each push or pop will cost you n operations. So the amortized cost will not be constant because all operations cost you n operations. So what we need to do? What you need to do is to make some gap between these two events. So what's the problem? The problem is you have the same position when you need to extend and when you need to decrease the size of the array. So the good implementation is to have two different words. So you increase the size when it's about the half of the array, and you need to decrease the size when it's not the half of the array, but let's say 1/4 of the array. Now what will happen? When you decrease the size of array, you have this. So you have 1/4 of all elements of the array. So here is n. And it's about 1/4 of the size of the array. Now when you decrease the size of the array, you have only half of the array field. So when you will need to extend the array back again, you need to add these n elements here. So you need to add another n elements to get to this point when you need to increase the size of the array. So you have about n operations between any two consecutive changes of the size of the array. So if you decrease the size of array, next time you need to increase the size of the array after the next n operations. Okay. Let's analyze it using the coins, for example. So how to analyze it using the accounting method? Now, let's prove that if we have these two functions, the amortized cost of both functions will be constant. Let's see. Again, let's put coins somewhere. So when we add elements to the stack, we will put coins on top of each element. So on each element, we will put coins of size 2. So when we need to increase the size of the array, we know that this right part is full with coins. So we have n over 2 coins of size 2. So we have n saved time. So we used these coins to increase the size of the array. Now we need to save some coins when we need to decrease the size of the array. So when we decrease the size of the array here again, we need to spend n coins here. So how to save another n coins? We will save these coins when we have pop operation. So each time we pop elements from the stack, we will save some coin. So when we pop these elements from the stack, pop, pop, we will put coins here. And we need to have enough coins to copy these elements to the next array. So we'll have n coins here, we'll have n elements here, so coins of size 1 is enough. So we have coins of size 1 on each empty element after we pop some element from the stack. So we saved n coins here. We just use these coins to copy these two elements to this new array. That's all. So we put coins when we push element to the stack, we put coins when we pop elements from the stack, and when we need to increase the size of the array or decrease the size of the array, we use these saved coins just to make this operation in zero time. That's all. Sometimes it happens when we have more coins than we actually need. So the total time complexity may be even negative. It's okay if the amortized time complexity is negative. It's totally fine. Because it's virtual, it's amortized time is something you come out with this. So it's not the function of your program. It's just something you just put. So it's okay if it's negative. If it's negative, it's again it's constant. That's all. Okay. Let's have the final thing I want to talk about. Final, very final. Last thing I want to talk about is how to make stacks of, or how to make queue of 2 stacks. What book do you recommend? I don't know any books by now. So there is a classical book about Korman algorithm analysis. It's kind of outdated, but it's good enough. You can read Korman. Korman is nice. I'll put a link in description, something like that. Final thing. Imagine you have 2 stacks. So you have stack 1 and stack 2. You just bought them on some sale on AliExpress, something like that. So you just have them. But you need a queue for your algorithm. So you somehow need to implement a queue. So these are 2 stacks. You can put elements here, and you want to be able to put elements here and remove from here. And you want to do something to make a queue from these 2 stacks. And very practical engineering, how to make this from this, you just split it in half. And say, these are 2 stacks. This left thing is a stack, this right thing is a stack. So I will have 2 stacks, and I get them from these 2 stacks. That's the idea. No task for today? No, we have tasks for today. No. We have tasks every week. And we will discuss the tasks tomorrow. No, it's all as planned. So how do you make it? Let's split the queue into halves. So we'll use 1 stack here and another stack here. That's all. How to add elements to the queue? If you need to add element to the queue, you simply need to add it to the stack 2. So that's 2 push x. So we add elements here, A, B, C. That's the plan. That's exactly what we will do. Now, You push the elements here. They are in the correct order. Now we need to pop elements, or remove elements from the queue. So how to remove elements from the queue? We need to remove them from stack 1. If stack 1 is not empty, we just remove the topmost element from the stack 1. If stack 1 is empty, we need somehow to put all elements from stack 2 to stack 1. So we need to get these elements and put them here. Let's just do it. Let's put all elements from this stack to this stack. How to do it? We just pop the elements from stack 2 and push them into stack 1. So we pop element C, push it here. Then pop element B, push it here. Then pop element A, push it here. So we just moved all these elements from this stack to this stack in the correct order. Let's say while not S2 empty. Just push S1, push S2, pop. Like it. So just move all elements from this stack to this stack. And now simply push the first element from the stack 1. That's all, that's the whole plan. Yeah. That's a queue. Now, let's analyze its time complexity. Again, some operations in this implementation are slow. What operations are slow? These operations are slow. So this while sometimes work in linear time. So if you push too many elements in stack 2 and then call remove, you may need to transfer all these elements to stack 1. And then this costs you a lot of time. But let's prove that amortized cost of both this operation is constant. So let's prove that amortized cost of both operation is constant. Now, how to prove it? No, the easiest thing is to prove it using the accounting method. I just erased it. Let's use accounting method. We need to put some coins somewhere, and then use these coins to make this long operation. Okay, so we need to look on this long operation. So what is this long operation? Long operation is when you take elements from stack 2 and transfer them to stack 1. To make these operations, we need to reserve some time. So we need to have some coins in our bank account and then use these coins to make this long operation. So where should we put these coins? Let's move back. So let's just put these coins on these elements of the stack 2. So when we push new element into stack 2, let's reserve some coin here on each element. So this push here will cost you two operations. First operation is to push element, and another operation to reserve this coin. So here the amortized time is 2. Now here we transfer these elements from here to here using these coins. So here all operations are free. We just take this coin, have some time stored in our bank account, use this time to move this element here. So here we spend 0 time. And here we spend another constant time. That's all. So the total amortized time of both operations is constant. And you may think about it using the potential method. So you can say that the potential of the potential function of this structure is just the size of the stack 2. So you may think about it like this. So we say the potential is the size of the stack 2. Then each time you decrease the size of the stack 2, so you decrease the potential, and use this the delta phi to transfer the element to the first array. Yeah, that's all. That's the same thing. I think that's enough for today.